Welcome to the lecture number 10 on linear programming problems under this course on computational mathematics with Sage Math. In this lecture, we are going to look at how to solve linear programming problems using Big M methods. Big M methods actually tries to combine two-phase simplex method in one phase, that is in one process. So we have seen that in case you have a linear programming problem in which initial basic feasible solution is not readily available, then we can use two-phase simplex method. In phase 1 we find out initial basic feasible solution, and then in phase 2 we find the optimal basic feasible solution. Now Big M method will combine the two phases together, right? So let us look at how we are going to do this. Start with the same standard problem, minimize C transpose X subject to Ax equal to B, X non-negative. Now what we are going to do in order to apply Big M method is we will add one artificial variable with each of this equality constraint. So there will be U1, U2, M artificial variables, non-negative artificial variables that will be added to each of these constraint, and then we will add a very large quantity times each of these artificial variable in the objective function. Why do we do that? Because like two-phase simplex method, in Big M method also, the main aim of introducing artificial variable is to obtain initial basic feasible solution. However, when you add these artificial variables to the constraints, it causes violation of these constraints. Okay, therefore we need to get rid of these artificial variables so that they do not appear in optimal simplex table. That is what we need to do. Okay, now so what do we do? As I said, to achieve this, that is to get rid of artificial variable from each of these constraint, we need to add a very large penalty which we write as M times Ui in the objective function, right? And then we apply this simplex method. Now once we introduce all these artificial variables and modify this problem, then this problem will look like something like this. What is it? It is minimize Z is equal to C transpose X plus capital M times summation Ui subject to Ax plus U is equal to B, and X and U will be non-negative. So that is the modified problem, which we call this as artificial problem, and we need to solve this problem and in such a way that the final solution should not contain U, right? That will give me the optimal solution of the original problem. Now let me give some remark, though we will not prove them, but let us just make a note of these things. One can prove this. You can look at some standard book on operation research where one can find proof of these facts, right? The first of these remark is that if an optimal solution is found with U equal to 0, then the corresponding X, right, the X which you have in the simplex table is going to be an optimal basic feasible solution for the original problem. Second result says that if for some constant M, positive constant M, an optimal solution is found but with U U non-zero, then the original problem will be infeasible. So what does it say? In case you have applied this simplex method and you have obtained the optimal solution, but this optimal solution also contains some artificial variable which is non-zero in the basic variables, then the original problem will be infeasible. We will see an example of this a little later. The next result says that if for some positive M, the approximating problem is unbounded, then the original problem is either unbounded or infeasible. Okay. Next result says that suppose that the original problem has a finite optimum value that let us denote it by V infinity, then Vm, and let Vm be the optimal solution of the approximating problem, then Vm is going to be less than equal to V infinity. Okay, and the next result says that for every capital M1 and capital M2, if capital M1 is less than equal to capital M2, then V capital M1 is less than equal to V capital M2. So what is V capital M1? V capital M1 is the optimal value of the artificial problem, and Vm2 is the optimal value of the artificial problem with respect to constant M2. The next result says that there exists a constant, positive constant M0, such that for some positive real number m greater than equal to m0, if V infinity is equal to m, right? What is V infinity? Value of the optimal value of the original problem. Then we can conclude that big M method will produce the right solution for large enough value of m, right? So in this case, if such things happens, then for large value of m, you can find solution of this using big M method. So these are some results. We will not look at proof of these results. Okay, now let us start with a problem which we will solve using big M method. So the problem is to minimize z is equal to minus 3x1 plus x2 plus x3 subject to x1 minus 2x2 plus x3 less than equal to 11, minus 4x1 plus x2 plus 2x3 greater than equal to 3, 2x1 minus x3 equal to minus 1, and x1, x2, x3 non-negative. Now if you look at this problem has all types of constraint. It is less than equal to constraint, greater than equal to constraint, or also equality constraint. So if you want to solve this problem using standard simplex method, we really have to kind of struggle to find the initial basic feasible solution. However, we can solve this problem using two-phase simplex method, right, that we have seen in the last class. So what we are going to do first, we will convert this problem into standard form. That means we have to make each of this inequality as equality. So in first constraint we need to introduce a slack variable which is x4. In the second constraint we need to introduce a surplus variable x5, and third constraint we don't need to introduce any variable because it is already equality type. Now the problem in standard form is as follows, right? Next, what we are going to do, we will now introduce artificial variable to each of these constraint. But however, if you look at the first constraint, in first constraint already x4 which we have introduced as slack variable comes with positive. Therefore, this x4 is equal to 11 can be taken as a basic variable. So we don't need to introduce artificial variable with first constraint. However, one can introduce that also, but it is not necessary. With second constraint, we will introduce one artificial variable u1. With the third constraint, we will introduce one artificial variable u2. So we will be introducing two artificial variables, u1 and u2. u1 with second constraint and u2 with third constraint. And then we will also modify the objective function by adding m times u1 plus m times u2. So let us write this revised problem, or that is modified problem or artificial problem. So this is the artificial problem or modified problem. So minimize z is equal to this original objective function plus 0 times x4 plus 0 times x5. The x4 and x5 are slack and surplus variable plus m times u1 plus m times u2, and subject to these constraints where u1 and u2 have been introduced in second and third constraint. Notice that in case your original problem is maximization type, and then in that case you may have to introduce this negative m times u1, negative m times u2. Okay, but however we will look at the problem which is minimization type, and we know that any problem can be converted into this form. So we will also always consider the problem in minimization form, and we will introduce this m times u1 plus m times u2. Okay, next let us in phase 2 simplex method, we will now get rid of u1 and u2 from second and third constraint. We will substitute the value of u1 and u2 from the second and third constraint in the objective function, and we will update the objective function. So it turns out that when you substitute u1 and u2 from second and third constraint in Z, it turns out that coefficient of x1 is minus 3 times 6m, coefficient of x2 is minus m plus 1, coefficient of x3 is minus 3m plus 1, and coefficient of x5 is m, and there is a constant term 4m. So now you can see here in this modified problem, now I can take x1 is equal to 11, u1 is equal to 3, and u2 equal to 1 as initial basic feasible solution, and that will give me the value of the objective function z equal to 4m. But m is very large quantity, so this is going to be a large quantity which we have to reduce. Right, now let us so we are going to apply simplex method, so we will need to pivot the matrix. So let me introduce this user defined function for pivoting and updating the simplex table. Okay, next let us write the coefficient matrix for this constraint and the objective function. So this coefficient matrix will also contain the right hand side and also contain the reduced cost coefficient. The reduced cost coefficient will be negative since it is a minimization type. We don't have to take the negative of the coefficient of x1, x2, x3. So the last row, which is the reduced cost coefficient row, will have coefficients minus 3m plus minus 3 plus 6m, minus m plus 1, minus 3m plus 1, 0, m, 0, 0, 4m. Right. Now let us create the initial simplex table. So when we create initial simplex table, I have not run this particular code. Okay, this also I need to run. So now let me run this. Let me run next one. So this is the initial simplex table. Right. Now if you look at this initial simplex table, the right hand side are all non-negative. So this is a feasible basic feasible solution. And then but the reduced cost coefficient, the values are 6m minus 3, which is positive for large m, but minus m plus 1 and minus 3m plus 1 will be negative. Therefore this is not an optimal solution. This is feasible but not optimal. Therefore we need to get rid of one of the basic variables to non-basic variables, and one of the non-basic variables we have to bring it to basic variable. So we will look at the reduced cost coefficient row, the one which is the most negative. In this case, minus 3m plus 1 is most negative. Therefore, this x3 will be incoming variable. Now we will look at the ratio of the right hand side by the positive entry in the incoming column. So that ratio is 11 by 1, which is 11, 3 by 2, which is 1.5, 1 by 1, which is 1. Therefore, minimum is going to be this, which is with respect to basic variable u2. Therefore u2 will be outgoing variable and x3 will be incoming variable. So let us now look at, so this is what is written here. So we will pivot now with respect to which row index. Row is 2 and column index is 2. So row 2 is, this is 0th row, first row, second row. So this is going to be this one, which is row number is equal to 2 and column number is also 2. So now let us update the simplex table, and when we update the simplex table, this is what we get. Now again, if you look at this stage, the value of the basic variables are x4, u1, u3. x4 value appears at 10, u1 is equal to 1 and x3 is equal to 1, and the value of the objective function will be minus 1 at this stage. Now if you look at this reduced cost coefficient row, again you have this is negative, minus m plus 1 will be negative. Therefore x2 will be incoming variable. Now look at the ratio of the right hand side by the positive entry in the incoming column. Therefore 10 by minus, this is we don't have to consider because this is negative. Next one is 1 by 1, so that is 1. This is 0, so that also we need to consider. Therefore, the ratio, only one ratio we need to consider, which is corresponding to u1 basic variable. Therefore, u1 will be outgoing and x2 will be incoming. So therefore, we need to pivot this. And the pivot row is going to be 1. Pivot column will also be equal to 1. So we will say pivot A 1 comma 1 and then update the simplex table. Now when you update the simplex table, what you see now, this objective, the reduced cost coefficient row, this x1 is -1, which is negative. Therefore, again, this is not an optimal solution. We need to bring x1 into basic and then look at the ratio. This is 12 by 3, that is 4, and the remaining are 0 and -2, so we don't have to consider. Therefore, x1 is going to be incoming, x4 will be outgoing, which is with respect to 0th index, 0th row and 0th column. Right. So therefore, we again update we apply the pivoting corresponding to row number 1 and column number 1, and then update the simplex table. This is what we get. Now you can see here, now the basic variables are x1, x2, x3. Non-basic variables are x4, x5, u1 and u2. And all the values in the reduced cost coefficients have become non-negative, because this is m plus -1 by 3, which will be positive for large M, and here capital M is also positive for large M, and the value of the objective function will be 2. Right. So this we have obtained optimal solution. Right. This is optimal solution, and it occurs at x1 is equal to 4, x2 is equal to 1, x3 is equal to 9, and the value of the objective function at this value will be -2. This here is minus z is equal to 8m plus 2, therefore z is -2. So that is the basic feasible solution, and it is optimal. So now you can see here, now in this final solution, final simplex table, none of the artificial variables are appearing. Therefore, all of them will take value 0, and therefore this is optimal solution. This completes big M method. Right. So that is how you are going to solve a problem using big M method. What are the steps? The first step is to write the problem into standard form, then introduce the artificial variable if required, then modify the objective function row, get rid of artificial variables from the objective function row, create the initial basic simplex table, and then keep on updating this till you get optimal basic feasible solution. Okay, and right. So let us solve this problem using inbuilt function. Right. So let us consider the same problem, and we will solve this using mixed integer linear program. By the way, you can also look at help on mixed integer linear program and then see how you can apply this particular function for minimization problem or problems involving other types of variables, which may have real, non-negative or integer, binary. All such possibilities are here. You can look at help on this. So let us solve this problem using this method. And when we solve this, we can see here the solution occurs at x1 is equal to 4, x2 is equal to 1, and x3 is equal to 9. That is what we obtained when we did step-by-step big M method, and the value of the objective function is -2. So that matches with what we did in this step-by-step big M method. Okay, now let us look at one more problem and see and apply, let us say, big M method to this problem. Again, this problem is of minimization type. The constraints are greater than equal to, and one constraint is equality constraint. So what we were going to do, first we will convert this problem into standard form. Therefore, the first and second constraint we will be introducing surplus variables x4 and x5. In the third constraint, we do not require any variable, artificial slack or surplus variable. Okay, now we will introduce artificial variables, one for each of these constraint. So we will introduce 3 artificial variables, u1, u2, u3, u1 for first constraint, u2 in the second constraint, and u3 in the third constraint, and then we will add m times u1 plus m times u2 plus m times u3 in the objective function, and then this modified problem will look like this. This is the modified problem or artificial problem. Now this again what is the next step? The next step is to find out value of u1 from the first constraint, value of u2 from the second constraint, value of u3 from the third constraint, and substitute in z. And when you do this and simplify, this is what you are going to get. The z is going to be 5 minus 7 m times x1 minus 6 times x2 minus 7 plus 8 minus 7 minus 8 m into x3, m times x4, m times x5, and plus 40 times m. Right? So that is what you are going to get. This will be the modified problem. Therefore, you can now again write the coefficient matrix A, which will include the right hand side and also the reduced cost coefficient row that will be at the bottom. So let us define this, and next we will create the initial basic simplex table. So that's the initial basic simplex table. So you can see here now objective function row has coefficients minus 7 plus 5, which is negative. Then this is also negative, minus 8m plus minus 7 is also negative, and so on. But the right hand side are all non-negative. Therefore this is feasible solution, but it is not non-optimal. So then we will need to bring in one of the non-basic variable to basic variable and one basic variable to non-basic variable. So how do we do that? We will look at the one which is the most negative reduced cost coefficient, which seems to be minus 8m minus 7, that is corresponding to the basic variable corresponding to non-basic variable x3. Therefore x3 will enter, and now we will look at the ratio. So the ratio here this is negative, so we don't have to consider. This is 20 by 10, which is 2. This is 5 by 1, which is 5. So the minimum ratio is 20 by 10 with corresponding to the basic variable u2. Therefore u2 will be outgoing variable and x3 will be incoming variable. And what is the pivot? This element is pivot, which is row number will be 2, column number will be 2. So we need to pivot A. Right, row number is 1, column number is 2. So we will pivot A, that apply pivoting A 1 comma 2, and then after that we will again update the simplex table. So when you update the simplex table, this is what you get. Again you can see here there are negative reduced cost coefficient. Therefore this is not an optimal solution, right? So which is the most negative one? In this case you can look at this minus 24 by 5 m minus 51 by 3 is the most negative one. Therefore x2 will be now incoming variable, entering variable, and then we will look at the ratio. This is one negative, so we don't have to consider. So we look at 21 divided by 16 by 5, and then other one is 3 divided by 8 by 5. And among these, if you look at the minimum ratio, that corresponds to basic variable u3. So u3 will be outgoing and x2 is incoming. So we will have to apply pivoting with respect to the third row and second column. So when we do that, that means pivoting A 2 comma 1, A is the third row, 2 means third row, 1 means second column. So when we apply pivoting, and now let us again write the updated simplex table, this is what we get. So again you can see here this is most negative. This one is again one negative, therefore we need to again find out the ratio, find out the incoming and outgoing variable. Now in this case the x1 is incoming variable, and look at the ratio. The ratio in this case will be minimum corresponding to basic variable x3. So x3 will be outgoing and x1 is incoming, right? Of course x3 had entered at some stage, so again it is going out. That can happen, right? So let us pivot this with the second row and first column, and when we pivot and update the simplex table, this is what we get. Now you can see here all the reduced cost coefficients have become positive, non-negative rather, and then and the right hand side is also non-negative. So this we have found an optimal solution for the modified problem. But then in this case, if you look at this u1, which is artificial variable, is appearing in basic variables, and it is taking value non-zero value 90 by 11. That means by one of this remark that this problem, though this problem has optimal basic feasible solution for the artificial problem, but it contains non-zero artificial variable u1, therefore this original problem is going to be infeasible. Right? The original problem will be infeasible. So now let us look at this problem using inbuilt function and then see whether it is infeasible. Right? So this is the problem which we are looking at. Now let us define this using mixed integer linear program and then try to solve this problem. And when we solve this, what does it say? When we try to solve this, you will see at the bottom it says that GLPK, the problem has no feasible solution. That means it is infeasible. Right? So you can see that in case you have solved this problem where the artificial variable appears with non-zero value in the optimal solution or the last stage of basic simplex table, then this original problem is infeasible. Of course, you can also look at an example where you will have unbounded revised problem or the artificial problem, and then you can see what happens to the original problem. That can also be explored, but you can take some examples. Anyway, so let me leave you with some exercises. So these are the 2-3 exercises which you can solve using Big M method. The first exercise is it involves two variables with three constraints. One constraint is greater than equal to and other two are less than equal to. The second constraint again of minimization type involving three constraints, and third one involves three variables and it includes greater than equal to and less than equal to equality. All of them are in. Okay, so thank you very much. In the next class, we will look at what is called dual of linear programming problem, and then we will try to develop a method to solve a linear programming problem using what is called dual simplex method. Okay, thank you very much.